In the complex chess game of international trade and technology, few moves have been as calculated or as revealing as America's recent consideration to cut off engine supplies to China's newest pride, the C919 commercial airliner. Earlier this year, multiple American news outlets reported that Washington was contemplating a dramatic step that could cripple China's aviation ambitions. The target? The engines that power the C919, a medium-haul passenger jet that represents nearly 2 decades of Chinese engineering determination and billions of dollars in investment. The C919 isn't just another airplane. It's a symbol of China's technological coming of age, a statement that the world's second-largest economy is ready to challenge the Boeing-Airbus duopoly that has dominated commercial aviation for generations. Since its inaugural commercial flight in May 2023, this aircraft has transported more than 1 million passengers across Chinese skies. It has logged 28,000 hours of safe flight operations, building a track record that airlines watch closely when making fleet decisions worth hundreds of millions of dollars. Industry observers believe it may only be a matter of time before the C919 joins Boeing and Airbus jets on international routes, flying passengers from Beijing to London, Shanghai to New York, Guangzhou to Sydney. But there's a vulnerability at the heart of this ambition, one that American policymakers have identified and, according to reports, are prepared to exploit. Every pilot knows that the engine is the heart of any aircraft. Without that heart beating reliably, even the most beautifully designed airframe becomes nothing more than an expensive sculpture. And here lies China's Achilles heel. Despite 17 years of development and remarkable progress in airframe design, avionics, and systems integration, the C919 still depends on American technology for its most critical component, the engines that generate thrust and keep it aloft. According to analysts tracking the commercial aviation sector, if the United States were to implement a complete embargo on engine exports, China's entire large aircraft manufacturing program could face production shutdown within just 3 years. The implications would be staggering, not just for Chinese aviation, but for the country's broader technological ambitions and its position in the global economy. Yet in this moment of potential crisis, an unexpected player has entered the stage. Russia, through its State Technology Corporation, has publicly offered to step into the breach. Sergei Chemezov, the general director of Rostec, told the Russian news agency Sputnik that Moscow stands ready to supply China with multiple types of aircraft engines, including their domestically developed PD-14. It was a statement that raised eyebrows across the aviation industry and in Western capitals alike. This declaration brings us to 2 fundamental questions that will shape the future of commercial aviation and international technology transfer. First, why would the United States risk antagonizing one of the world's largest aviation markets by threatening to cut off engine supplies? And second, can Russia's offer genuinely solve China's engine problem? Or is this merely diplomatic posturing that will crumble under the technical and commercial realities of modern aircraft manufacturing? Before we dive deeper into this unfolding drama, if you're interested in stories about technology, geopolitics, and the forces reshaping our world, please subscribe to this channel and click the notification bell. We bring you in-depth analysis on the trends and conflicts that rarely make headlines but shape the future we'll all inhabit. Now let's explore how we arrived at this critical juncture. To understand the vulnerability of China's C919 program, we need to travel to an industrial zone south of Paris, in a region known as the beating heart of global aviation manufacturing. This is Villeroche, home to one of the world's most sophisticated aircraft engine facilities. Here, on a sprawling campus covering more than 100 hectares, equivalent to roughly 140 soccer fields, sits the crown jewel of Safran Aircraft Engines and a production hub for CFM International. The Villeroche complex is not just large, it's a marvel of modern industrial organization. Within its boundaries work more than 5,000 employees, research engineers pushing the boundaries of materials science and thermodynamics, precision assembly technicians who can measure tolerances in microns, supply chain coordinators managing thousands of parts from hundreds of suppliers, and after-sales service teams that support engines flying on every continent. Together, they form one of the most complete and efficient aircraft engine production ecosystems anywhere on Earth. The output of this facility is staggering. Each year, Via Roche produces upwards of 1,600 aircraft engines. These power plants go on to propel more than 800 new aircraft as they enter service with airlines around the globe. When you look at the commercial aviation market today, you find a remarkable statistic: more than 70% of all single-aisle jets currently carrying passengers, the workhorses of short and medium-haul routes that form the backbone of global air travel, are equipped with engines that originated from this French facility. The C919, China's challenger to Boeing's 737 and Airbus's A320, could not escape this reality. In 2018, the Commercial Aircraft Corporation of China, known as COMAC, signed a substantial agreement with CFM International for 760 LEAP-1C engines. These power plants were specifically designed for the C919, optimized for its weight, aerodynamics, and performance requirements. That order represented enough engines to power approximately 380 aircraft, a significant commitment that reflected China's ambitious production plans. So far, around 18 C919s have been delivered to Chinese airlines and are flying commercial routes. Simple mathematics tells us that roughly 360 LEAP-1C engines remain in the pipeline, awaiting delivery. These engines represent not just hardware, but the future of China's commercial aviation program over the next several years. Safran understood the strategic importance of this relationship. Last year, company executives made clear that if the C919 achieves true mass production, meaning hundreds of aircraft rolling off production lines annually, they would seriously consider establishing a dedicated LEAP-1C assembly line on Chinese soil. This wouldn't be unprecedented. Safran had already opened an assembly facility for the LEAP-1A variant in Tianjin with an initial capacity of 50 engines per year. It was a statement of confidence in the Chinese market and a bet on the C919's commercial future. But here's where the story gets complicated, where corporate strategy collides with geopolitics. CFM International, despite its French-sounding name and its critical manufacturing presence in France, is not purely a European company. It's a joint venture, a 50-50 partnership between France's Safran and America's GE Aerospace. Each partner holds equal stakes, equal decision-making power, and critically, equal veto authority over major decisions, including who receives engines and who doesn't. This corporate structure means that regardless of French commercial interests or European trade policy, if Washington decides to impose sanctions on Chinese aerospace companies, it has the legal authority and political leverage to force CFM International to halt engine deliveries. And as events this year have demonstrated, this isn't a theoretical concern. It's a reality that has already begun to unfold. When the warning shots were fired, the first clear signals came in late May of this year. The United States Department of Commerce, which oversees export controls on sensitive technologies, made a carefully worded announcement that sent ripples through the aerospace industry. The department stated it would consider suspending export licenses for certain American companies that supply products and technologies to COMAC. In the language of international trade, consider often means have already decided, but are managing the announcement carefully. And indeed, what followed suggested this was more than idle speculation. Within weeks, numerous American suppliers, companies that had maintained successful, profitable relationships with COMAC for years, found their applications for new export licenses summarily denied. CFM International, the supplier of those critical LEAP-1C engines, was among the companies affected. The implications were immediately understood across the aviation industry. The United States was prepared to use engine supplies as a pressure point in its broader technological competition with China. But the threat extends far beyond engines alone. When you examine the C919 supply chain, you discover just how deeply American technology is woven into this supposedly Chinese aircraft. Beyond the CFM engines themselves, American companies provide numerous critical systems. Rockwell Collins and GE collaborate on the avionics suite, the complex computer systems that manage flight controls, navigation, and communication. Raytheon supplies communication and navigation equipment. Parker Hannifin delivers hydraulic flight control systems that translate pilot inputs into aircraft movements. Honeywell provides the auxiliary power unit, which generates electricity and compressed air when the main engines aren't running. Even the landing gear hydraulic systems come from Parker Aerospace. Each of these components is essential. An aircraft cannot fly safely, indeed cannot be certified to carry passengers, without functioning versions of these systems. They represent hundreds of millions of dollars in research, decades of accumulated engineering knowledge, and exacting standards that few manufacturers worldwide can meet. Although American officials haven't publicly specified exactly which components have had their export licenses suspended, and although international media reports remain somewhat vague on specifics, the message is unmistakable. The United States possesses multiple pressure points on the C919 program, and it has demonstrated a willingness to use them. Some American media analysts have made stark predictions. If the United States fully implements an embargo on LEAP-1C engine supplies, cutting off both new deliveries and potentially spare parts and maintenance support, the C919 could be forced to cease production within 36 months. That timeline reflects the current inventory of engines already delivered, the aircraft in various stages of assembly, and the lead times required to develop and certify alternative power plants. This brings us to a crucial question. Why would Washington take such a dramatic step, one that risks not just Chinese anger but also significant commercial losses for American companies? To understand America's calculus, we need to look beyond aviation to a different class of materials that has become central to 21st century technology: rare earth elements. These 17 metallic elements with exotic names, lanthanum, cerium, neodymium, europium, dysprosium, and others, possess unique magnetic, luminescent, and catalytic properties that make them indispensable in modern technology. Your smartphone contains rare earths in its screen, speakers, and vibration motor. Electric vehicles use powerful permanent magnets made from rare earth elements in their drive motors. Wind turbines rely on rare earth magnets for efficient electricity generation. Military applications, from fighter jet engines to guided missile systems to advanced radar, depend heavily on these materials. And in this critical supply chain, China holds a position of almost complete dominance. While China possesses roughly 37% of the world's known rare earth reserves, significant but not overwhelming, it controls more than 90% of global refining capacity and possesses virtually all the advanced processing technologies. In the category of heavy rare earths, which includes some of the most strategically valuable elements, China stands alone. It is the only nation on Earth with complete capabilities for separation and purification of these materials at commercial scale. For the United States, this creates an uncomfortable dependence. More than 70% of rare earth compounds used in American manufacturing are imported from China. When it comes to heavy rare earths, American dependence approaches 100%. Despite years of talk about diversifying supply chains and developing domestic processing capability, alternative sources remain inadequate. Recognizing this strategic leverage, China has increasingly used rare earth exports as a geopolitical tool, particularly in response to Western technology restrictions. Over the past 2 years, Beijing has progressively tightened its rare earth export policies. Just 1 month before the United States announced its consideration of restricting C919 engine exports, China implemented another round of enhanced controls. Under the new regulations, any company seeking to export rare earth materials must obtain a license from Chinese authorities. More significantly, applicants must provide detailed information about the final use and ultimate customer for the rare earth materials. While exports for civilian applications in automotive and electronics sectors remain possible, anything with potential military applications faces stringent scrutiny and, increasingly, outright rejection. The impact on American defense contractors has been immediate and severe. Although many companies initiated urgent efforts to find alternative rare earth suppliers outside China, the reality has proven far more challenging than anticipated. One manufacturer producing drone components for the Pentagon revealed that despite multiple rounds of negotiations with suppliers in other countries, they failed to secure adequate rare earth materials. Critical defense orders were delayed by 2 months as a result. Perhaps even more concerning than supply disruptions has been the price volatility. When Chinese export controls tightened, markets reacted dramatically. By mid-June, the cost of certain magnetic materials had increased more than 5-fold compared to prices before April. Samarium, a rare earth metal crucial for fighter jet engines, saw its price spike nearly 60 times its previous level. Such price shocks send ripples through entire supply chains, affecting cost calculations for major defense programs and forcing difficult decisions about project timelines and capabilities. Faced with this economic pressure and the very real possibility of defense production disruptions, the United States found itself in an uncomfortable position. The leverage it sought to apply against Chinese aviation suddenly seemed to cut both ways. On July 4th, America's Independence Day, perhaps not coincidentally, the U.S. Department of Commerce officially approved GE Aerospace to resume supplying jet engines to COMAC. Simultaneously, several American original equipment manufacturers received permission to gradually restart component deliveries for Chinese aircraft projects. The attempted pressure campaign, at least in its initial form, had been walked back. Even if American resolve had held firm, implementing a complete technology embargo would have carried significant costs for the United States itself. Beyond the immediate risk of breaching already signed procurement contracts, which could expose American companies to substantial financial penalties and legal challenges, the primary casualties would have been the American aviation suppliers currently fulfilling orders. These companies have spent years, sometimes decades, building relationships with Chinese aerospace manufacturers. They've made significant investments in understanding Chinese certification requirements, establishing local support networks, and adapting products to Chinese specifications. The Chinese aviation market, already the world's second largest and projected to become the largest within the next decade, represents future growth opportunities that no aerospace supplier can casually abandon. More fundamentally, if the United States genuinely intends to slow or halt China's commercial aviation development by cutting off engine supplies, history suggests the strategy might backfire spectacularly. Rather than abandoning their aerospace ambitions, the Chinese would almost certainly respond by accelerating their efforts to achieve self-sufficiency in critical aviation technologies. Western restrictions don't tend to make China give up. They make China more determined to develop indigenous alternatives. Although the United States eventually reversed course and resumed engine technology exports for the C919, few observers believe this represents a stable, long-term resolution. The resumption appears tactical rather than strategic, a temporary accommodation to address immediate rare earth supply concerns. The underlying tensions remain, and the threat of future restrictions hangs over the C919 program like a sword suspended by an increasingly frayed thread. It's against this backdrop of uncertainty that Russia's offer acquires significance. Last month, Sergei Chemezov, the general director of Rostec, Russia's massive state technology corporation, made a public statement that captured international attention. Russia, he declared, stands ready to supply aircraft engines to China. If Beijing has need, Moscow has solutions. This wasn't empty posturing. Rostec is among Russia's largest and most capable industrial conglomerates, with deep expertise in aviation technology. Its subsidiary, United Engine Corporation, ranks as the world's fifth-largest aircraft engine manufacturer, trailing only GE, Pratt & Whitney, Rolls-Royce, and CFM International. The company maintains a comprehensive product portfolio spanning various engine types, from regional aircraft power plants to engines for long-range wide-body jets. Currently in production are the PD-14 and PD-8 engines, both modern turbofan designs that power Russian commercial aircraft. Under development is the PD-35, an ambitious project aimed at the long-range wide-body market currently dominated by GE and Rolls-Royce. In the military aviation sphere, Russian engine technology is particularly strong, with capabilities that rank second globally, exceeded only by the United States. The PD-14 that Chemezov specifically mentioned represents Russia's most recent achievement in commercial engine technology. It's the first high-thrust turbofan engine developed entirely within Russia in recent years, without dependence on Western components or technologies. The PD-14 meets modern standards for fuel efficiency, noise levels, and emissions, the benchmarks by which commercial engines are judged. Currently, the PD-14 powers the MC-21, a Russian medium-haul jet designed explicitly to compete with the Boeing 737 and Airbus A320. The MC-21 targets the same market segment as the C919, flying similar routes with comparable passenger capacity. In theory, this makes the PD-14 a logical alternative should American engine supplies become unavailable. But theory and practice in aviation often diverge dramatically. Integrating a different engine onto an existing aircraft design is not like swapping batteries in a flashlight. The engine is intimately connected to virtually every major aircraft system. Its physical dimensions determine the wing structure and landing gear height. Its weight and thrust characteristics affect the aircraft's balance and performance envelope. Its fuel consumption patterns influence range calculations and airline operating economics. Its maintenance requirements determine service intervals and support infrastructure needs. Adapting the C919 to accept the PD-14 would require extensive redesign, recertification, and testing, a process requiring several years and hundreds of millions of dollars. Airlines that have already ordered C919s with LEAP-1C engines would face difficult decisions about whether to wait for the redesigned version or seek alternatives from Boeing or Airbus. The entire timeline for the C919 program would slip significantly. Moreover, Russian engine technology, while respectable, doesn't quite match Western standards in some critical performance parameters. Fuel efficiency, maintenance intervals, and operational reliability, the factors airlines scrutinize most carefully when calculating lifetime operating costs, favor Western engines. For the C919 to compete effectively in international markets, where airlines make sophisticated economic calculations about total cost of ownership, engine performance matters enormously. There's also the question of production capacity. Even if China decided to adopt Russian engines, could Russia manufacture them in sufficient quantities? The Russian aviation industry, though technically capable, operates at a much smaller scale than its Western counterparts. Producing hundreds of engines annually, with the quality, consistency, and after-sales support that commercial aviation demands, would strain Russian manufacturing infrastructure. So while Russia's offer isn't meaningless, it represents a potential fallback option in a worst-case scenario. It's not a simple solution to China's engine vulnerability. Chinese engineers and policymakers understand all of this. They've known for years that true independence in commercial aviation requires indigenous engine technology, and they've been working toward that goal with characteristic determination. As discussions about potential Western supply cutoffs intensified, a Chinese engine designated the CJ1000A has gradually moved from classified development program to public knowledge. Public information about the CJ1000A reveals it as China's most serious attempt yet to develop a commercial turbofan engine capable of powering large passenger jets. The specifications are promising. The CJ1000A is designed to produce approximately 13 tons of thrust, placing it in the same performance class as the LEAP-1C it's intended to replace. It incorporates composite fan blades, lightweight, strong components that improve fuel efficiency and reduce noise. It uses digital control systems that optimize engine performance across the flight envelope. According to Chinese engineers, its fuel efficiency has already approached the levels achieved by the LEAP series, the gold standard in its class. The engine has passed significant technical milestones. It completed a 150-hour core endurance test, subjecting its hottest, most stressed components to conditions simulating extended operation. It has been mounted on a C919 test aircraft for high-altitude flight trials, the crucial step of validating performance in actual operating conditions, rather than test cells on the ground. The target timeline is aggressive. Chinese authorities aim to complete airworthiness certification for the CJ1000A before the end of 2026, with mass production beginning in 2027. This schedule is 3 years ahead of the previous expectation that a Chinese commercial engine wouldn't enter service until around 2030.